Hi and welcome to the Yosys Users Group Meetup number 9. Yosys Users Group Meetup happens about once every 6 to 8 weeks, and if you're interested in joining the next one, then you can sign up to the mailing list. I'll put the link down below in the description. In the past, we've covered things like system Verilog, plugins, hardware security, and today we're looking at FPGAs. We're going to take a look at the Synth ICE 40 flow, and our own Krystine from Yosys HQ is going to be taking us through what happens from your Verilog through to the bitstream. So grab a cup of your favorite beverage, settle in, and enjoy the talk.
Cool. So we do have a bit of a demonstration kind of presented as a Yosys script. So if you are familiar with Yosys, Yosys is able to run scripts, and kind of the ICE 40 or the Synth ICE 40 command is itself kind of a script in turn. But to kind of to start off with, what is synthesis? So essentially what we're doing is we're taking some kind of HDL input. In this case, we're going to be looking at a Verilog design, and then mapping that design, the logic in there, onto hardware elements. In this case, for the ICE 40 platform. But the kind of overall process is fairly generic. And so we're going to be kind of using this as just a demonstration of that, and getting some platform-specific output. So we're going to be using JSON, which could then be used for next PNR to actually put it on the hardware. So yeah, Synth ICE 40, synthesis command for the ICE 40 platform. Most of the FPGA synth scripts use a lot of the same parsers, and even for some of the ASIC flows, the kind of initial part of that is also going to be quite similar. If you kind of want to see what is happening, what I've done is, so if there's anything that starts with the $sign in here, it is a command line kind of command. So you can run the help Synth ICE 40, and so that'll print the help output there. Or if you're in a Yosys shell, which we'll get to later, you can run that directly. There is also on the documentation a page for that. So I will just bring that up quickly. Yeah, so this is the same thing. The command reference documentation is generated from Yosys. So as long as you're using the same version of Yosys, this will be the exact same thing you would get on the command line if you were to run help Synth ICE 40. And so what we're going to be looking at today is this part down here, where we've got the following commands executed by the synthesis command, and going through each of these steps, seeing what some of the commands do, and looking at the circuit. So the demo that we're going to be using is available in the Yosys source repository under the docs. So this is the same example FIFO that is used in the synthesis data available there. It is just a simple FIFO ring buffer with parameterizable memory size. So it's this FIFO.v over here. So we have two modules. We have our address generator and the FIFO itself. So the FIFO is just some memory, two address generators, one for the reader and one for the writer, and then it kind of loops around, incrementing either the read or the write, depending on which enables are high. And so kind of our goal for today is we want to run this command, and there we go, we're done. Time to go home. So that's it. But no, we're going to be stepping through what that's just done. But essentially what we've done there is we've loaded in our FIFO.v. We've called Synth ICE 40. We've specified that our top module is FIFO, and we want to output to a JSON file, FIFO.json, which, as I said before, we can then use for next PNR. So yeah, we're going to be stepping through that script that we saw before, and I've got just that bit of the text cut out here to make it a bit easier to look at as well. And so yeah, we're going to be looking at kind of the common things used across synthesis passes and where changes are happening in our design using the show command. So our first step, we have a Yosys shell prompt. So if you just type Yosys on the command line, you will get a shell prompt like this. And so using this, you can then enter in whatever command you want. So we have that help synth ice4d, and there we go. We have that full list of commands there as well, and it does have everything else that's happening in there, like what options are needed, all the things like that. But if we come over to the synth ice4d command, the first thing, we've got this begin block. So this is the elaboration step. So what we're doing, we're running this part of the command. So again, we've got that synth ice4d specifying the top module, and we can specify this run argument, and we can say we want to start at begin and end before flatten. So we're just running this part here, or I guess yeah, this part here. So looking at what that does, so we have this first read verilog command, and we're loading in this ice4d specific library cells_sim.v. And so what that does is it gives us all of the cell models for the IP blocks. So anything like your PLLs, any kind of hardware specific things that you're using. I think I might put them to do that. And so yeah, anything, if you're using hardware IP, you're going to need that. And it's kind of important to run that before the hierarchy. But that will also be used later for once things start getting mapped to actual hardware as well. So the first thing you want to do when you start loading a design is to call hierarchy. So this, we're specifying our top module. So this just says, okay, well, we have this hierarchy. Our top module is FIFO, and kind of we want to check that everything is as expected. So that'll do some kind of sanity checking and make sure that there aren't any errors in our design, and it's not missing anything that it expects to be there. And so then once we've done that, because we have in here, we have some always blocks. These get converted into processes in that read verilog. So we can run proc, which runs a bunch of things and converts the processes into actual logic that we can then kind of work with. So if we run stat on that now, we can see, okay, well, we've got 0 processes. We have a memory for our FIFO data, and we have a bunch of cells here that are being used for our design. So we can save that in case we want to come back to it later, but that and the stat is not actually part of the kind of general flow. That's more for me so that I can come back to it if I need to. So what we can do now is show that design. So if we look, we have this wonderful show command that we can look at. So we have at the bottom, this is the name of the module. So we're looking for something with the name addogen in it. And because this is a module with parameters and it has been instantiated for use in the FIFO module, it gets this automatic name, so saying that it's a parametric module named addogen with the values for the parameters. So in this case, we're setting max data to 256. And we've done some highlighting of cells here. So we have an add and an equal in blue, and some over here in pink. So if we look at our FIFO.v, Our blue, we have an add for the address +1, and we have an EQ, which compares if the address is equal to max data -1, which in 8 bits, so 256 minus 1 is 255, which is 8 bits of 1, which we can see here. So we've got that EQ. And then the mux says, okay, well, if they are equal, then we need to reset to 0. So we reset to 0, or we set it to the current address +1. And then this is kind of that feedback loop of what this is all doing. So yeah, you've got the actual register there at the end with reset and clock and the data input. Cool. So skip over that bit for time. So our next kind of thing that we have is this flatten step. So again, we're kind of looking at starting with flatten and ending before coarse. So we want to first run flatten. So what that's doing is it's taking our address generator module and replacing it in our overall design with the contents of that module. So in FIFO.v, we have these two module instantiations for the FIFO writer and the FIFO reader, and both of those have now been replaced with the actual module itself. And we have then two extra commands, which don't do anything for this design, so we're just kind of going to skip over them. But if you did want to learn more about them, you can look at what it's doing there or on the documentation on the website. And we can now look at our kind of bigger picture here. So we have the same circuit that we had before. We've got our muxes and our adds and our flip-flop, but it is now in the bigger scope of the FIFO. In this case, we are just looking at...
The show isn't showing, Krystine.
Sorry, thank you. So yeah, we've got in pink here the address generator, specifically for the FIFO reader, and we're looking at just the input cone for our R data. So in the select semantics, so we're looking at O:(R data and its entire input cone, and then we're highlighting the inputs to the FIFO reader address signal without the two input signals. So this is kind of what we're going to be focusing on, because if we look at the whole design, even at this stage, it is rather large. And if you do want to learn more about the selection syntax there, I'm not going to cover it here because there is a lot to it, but again, it is on the documentation and you can do help select. Cool. So our next step, we get into the big chunky coarse-grain representation. So we have this big block here for the coarse. So this is, we now have all of our kind of logic and everything is in the internal RTLIL format, and we can operate and optimize around that. And so at this stage, all of our cells are in their coarse-grain representation. So what that means is that each cell can operate on multiple bits rather than on individual bits, which we'll get to later. And they are all variable width, so a single add cell might be able to have anywhere from 2 to 32 bits of input and output. So our first part here is just do some cleaning, getting rid of anything that is unused, and doing a little bit of optimizing of expressions for constant folding. If we had any FSMs, this is where we would pick them up. We don't, so again, we're going to just skip over that command, but the FSM command does expect the opt command to be run before it with these particular options, so that the flip-flops are in the right configuration in order to be most easily detected for FSMs. And then after that, we then rerun opt, which is kind of the general optimization pass. So if we have a quick look at that, so what it does is it calls all of the other opt passes in this order, and it kind of loops through this main block until there aren't any more changes happening. Cool. So then we can checkpoint that in case we need to come back to it, and have a look now at the show command. So this is again what we were looking at just before, but it has been optimized, and so we now only have a single MUT cell rather than the two that we had before. And yeah, it's just much smaller and compact. So the next part of the coarse grain representation that we've got, W reduce. So we have operator width reduction. So in our add, this is a 32-bit add at the moment. So we have an 8-bit signal coming in for the reader address, and we have just a 1, which typically means that it's potentially 32-bit signal, but we're only actually using 8 bits of that output. So what W reduce will do is it will take all of the extra bits that we're not using and just get rid of them. So we've got, here we go, the top 23 bits of that add cell have been removed. So we're only using the lower bits of that. So we have a couple more optimizations. Yeah, if you want to look at them in more detail, you can. So the share pass basically is using some SAT-based resource sharing to try and see, are there any resources that we're using in different cycles. So this is quite useful in like pipeline designs where you might have an adder that is only being used in one pipeline stage, and it can then be reused in others if you only have one thing in the pipeline at once. And we've also got some more optimizations here. So we want to run this tech map script, so mapping our comparison operators into lookup tables. And so for the ICE40, we have 4 input LUTs. So we specify that our LUT width is 4, but we do have this generic CMP2 LUTs script. And so anything with a plus here is in the share directory. So if you are in Yosys and you have built, it is in share. So we just have this, yeah, there we go, comp2 LUT. And so this is what that is loading. And there's a whole bunch of TechMap specific code in there that we're not going to get into. But that is kind of, yeah, what that is doing there. So we can then run that. And next up we have memory DFF. So this is merging our input and output DFFs into memory read ports. So if we open up our show command again, so we have this mem read cell here with a DFF on the output. But having just run memory DFF, we can see, okay, well, the read port is now merged into the cell, and it is non-transparent. So yeah, we'll get to looking at that in a minute. In the meantime, we will combine our arithmetic cells, so ALU-MAC, combining all of our adds and subs and everything into either an ALU or a MAC, so multiply, accumulate. This just helps with kind of simplifying the mapping to the hardware and making sure it's easier to optimize things if they're all in a unified format. And we can then opt and design save. So if we run this, here we go, we now have a memoried V2. So this is that combined cell with both of them, and up here we have an ALU that has replaced our add, but is still doing that same kind of the address +1 into the mux back into the flip-flop. And so this memoried V2 is currently it's an abstract memory cell. So if we were to run stat here, we can see that we have a single memoried V2 and a single memwrite V2, and we have one memory with 48 bits of memory. And so essentially what these two cells are doing is that they're kind of abstracting away the actual memory. So we have independent reads and writes to a shared memory that is being kind of maintained in the internal language of Yosys, but is not yet physical hardware, which is what we resolve next. And so we have this memory no map. So we're combining our memories, but we're not wanting to map them to hardware yet. We can then clean and stat, and so we now have a single memv2 cell, 0 memories, 0 bits of memory. And if we look at that, yeah, we now have this memv2, which has both the read and the writes in a single place. Still ignoring the writes, just because it gets a bit messy. And there we go. Yeah, we got the memv2. So ignoring the writes, and just to keep things small and easy to read. But the next step in our synth ICE40, we have map RAM and map FF RAM, so flip-flop RAM. And we're going to now be taking that memv2 and mapping it to the hardware available on our ICE40. So the way we do that is with this memory libmap command. So if we come back to here, we do that, we convert our memv2 into an ICE40 RAM 4K. We then run the next two commands, which takes that still an internal cell and maps it to the actual hardware. So if we look now, we have this wonderful little SB_RAM40_4K, and that is now the actual hardware IP block that is in the final design. And so that RAM it's all done now. If we look at it, the select statements here are starting to get a bit messy, but that is to kind of help keep things visibly much simpler. So we've got our SB_RAM44K, and we have this little thing on both the input and the output, often referred to as swizzling, where kind of different the bits in the output and input have been reordered in order to optimize for the memory itself. So for example, over here, we've moved our 0th bit of the address has now become the 8th bit of the address in memory. And yeah, that's kind of platform specific and is configured through that memory libmap in the lib kind of setup. That's all controlled through that text file there, which you can look at if you want to. So next up, we have the map FFRAM. So if there are any leftover memories that weren't able to be mapped to hardware, they just get mapped to the logic fallback, which is flip-flops. So we can run that. No changes for our design because we only had that one memory block and it did map to the hardware. But next up, we have arithmetic. So now what we're doing is we're converting the arithmetic to gate level primitives. So if we look here, we have we have our ALU cell we have DFFs and EQs and ANDs. So if we look at the AND, we have a $1 lowercase AND. Once we do this, we end up with $3 underscore uppercase ANDs. And so what we've done is we've exploded our multi-bit cells into multiple single-bit cells. For ICE40, we also get a special wrapper for the carries. So like we had with the memory, where we had kind of that mem read and mem write, we have these ICE40 carry wrappers, which are abstracting away the physical hardware, but is implementing in a way that Yosys understands how those carries are connected internally. And so that gets done from this TechMap arithmap.v. And if we look, because we now have split up our cells into per bit, we want to kind of, we want to look at the individual bit. So we're just going to pick the third bit. But in order to look at the individual bit, we have this splitnets command. So what that does is it splits up multi-bit signals, and we also opt clean to get rid of anything we don't want. But at the end, we will revert back to before those changes, just so that we can see what the synth ICE40 command is doing without our kind of interference. But we can run that, and what we get is this little circuit here. So we now have just the third bit of the read address. So it's stored in this difficult to say name, which if we were to look up, we help $_DFFE _PP0P _. There we go. It is a positive edge D-type flip-flop with positive polarity reset and positive polarity clock enable. And so, not only do we have help for the commands, but we also have help for cells. And if you add a plus to the end of it, then we get the Verilog model, which you can use, or is also used internally for the Yosys simulation things. We've also got the series of not, or, and mux. So these ones in blue, what was previously our EQ cell has been split up into the series of gates, and going into the mux at the end. If we go to our next step, so we are mapping our flip-flops. So back in our ICE40, we are now down to map FFs. Are we? I missed a step in here. Interesting. That's fine. So we're down to map FFs. So we've got this DFF legalize, which converts all of the DFF cells into only the cells that are supported on hardware, and then we map that to hardware. And any other cells, we use simple map to convert into gate level primitives. Also, so we're running this ICE40 _opt-full. What I've done is I've added this debug command to the start of it. So we're saying run this command with debug output enabled. And so if we do that, we can see up here, there is this replacing mux cell. So if we look at the output, this is the cell over here. We're replacing that with, because it has a constant driver of a 0, a mux with a 0 is just an AND gate. So we can replace that. And if, yeah, we skip the looking at it, but yeah, that's just an AND gate. So it replaces that to optimize it. And so what we've also done there is we now have these SB underscore DFFs. So again, without the $ and with the SB prefix, that is the physical hardware. We do have a pair of the scope info cells. Those won't get mapped. Those, if we look at them, we select type scope info. Those are our two modules that were in the flatten part. So we have our FIFO reader and we have our FIFO writer. Cool. So the next step is to map LUTs. So this is converting our gate level primitives to lookup tables or $ LUT cells. So here we are using the ABC9 command. If we look at the synth ICE40, actually no, if we look, yes, I think this is a simplified version. If we look at the actual ICE40, so there's in here, we have some kind of optional parts. So because we're using the ABC9 method, we do get that ABC9 over here. But there are alternatives to that. So you can run here no ABC, or you can run ABC twice, or you can use ABC rather than ABC9 because those are two different things, depending on the version of ABC, all of which there is more information about in the documentation. But when we do run that ABC command, we lose some of the internal information that we had before. So where before we could look up just the FIFO reader address by name, we can't do that anymore because that does kind of get lost in that translation and optimized away. But the next step we want to do is unwrapping our carries. So if you remember, we have these ICE40 carry wrappers. And so those are the abstracted representation. And at this stage, we are down to just carry wrappers and LUTs after we did that tick map to convert all of our ands and ors and everything into LUT cells. So we want to, let me just run all of that. And we're now down to, we've gotten rid of those carry wrappers. We've replaced them with SB underscore carries and LUTs. And at this stage, we're getting pretty close. All we've got left really is to map those LUTs down into the hardware. So if we do that, that's all gone. We just have those two scope infos. And if we look again at that memory feedback path, we can see over here, we've got a flip-flop going into a LUT and then back into the flip-flop. So that is one of our address bits for the read address with a carry input is being concatenated together, and then input into a LUT4 with another carry, with the same carry input, and then feeding back. And that's it. So if we were to show FIFO, it takes a minute because the design now is rather large, but this is all of the hardware that is being used. So all of these LUTs and everything's mapped directly to hardware. There is our memory cell from before. Each of those bits is then separated out into its own set of logic. And you can go in and you can follow that and see what's happening there. But for our purposes, yeah, the final thing in there is this check step. So like it says, that is really just checking everything is kind of correct, that we haven't lost anything along the way, and that the design still makes sense as far as the Yosys is concerned. And so we can just run those. That last one, replacing any white box modules that we still have with black box modules, since in hardware it doesn't matter. And then our final thing is we can write JSON to our output JSON file, and then use NextPNR or whatever other tool to take that JSON input, which is just describing this kind of the same thing that this diagram is, and we can then write that down to hardware, and do the place and route that is involved there. But yeah, that is the synthesis flow. If there are any questions, please feel free to ask. That's all I've got.
Thanks very much, Krystine. Great presentation. So yeah, if you have questions, either raise your hand so we can call on you to ask, or just drop a question in the chat. And let's all give a round of applause for Krystine. It's a standing ovation. Okay, got one from Joshua. What do the text files contain?
So are you meaning for the libmap? Where is it? These text files, yeah. Cool. So we can open the actual. Do you tell me? No, you don't. So there is a page on the documentation about kind of the format of those text files. If somebody could find that link, Nat. But we can, if we just look in there, so again, that is in, so the plus means it's in the shared directory, and then ICE40. So for example, we have yeah, so that's this specific text file. So that, but I mean, for the format of that, like memory libmap is expecting, there is a page on that. I believe, let me see. So if you go onto the Yosys documentation, it's under, where is it? I think it's Yosys, using Yosys advanced synthesis and detailed memory handling. So I can chat, there we go. So that is the page. So that is kind of what's in that text file, but essentially it's just describing the underlying block. And so if there were multiple options, it would have each of those different options and the corresponding costs to them. This particular kind of memory, when we did this step, it was some additional output logic added because, yeah, let me see if I can. The design mode course. So, yeah. Go back again. If I debug that, so we can see in there, it is emulating read first behavior. So in our FIFO.v, we have specified that we read and write in the same cycle, which means that we are reading before that write finishes. So there are kind of a couple of different options there in terms of what the hardware could be doing. It could be read first, write first, or transparent, so it can pass through the write directly to the read. But so the memory lib map pass will, if necessary, emulate that logic to make sure that the semantics match. And so that this file helps to make sure all of those things happen and that our the design that we have created matches the actual hardware mapping. So if we actually look in here, there is also under this debug kind of version, we can see that we have this logic fallback. So it does have a cost associated with it. If that cost was lower than the cost for the physical hardware, then it would use that logic fallback. Otherwise, if you had, I'm not sure specific examples, but for example, if you did have kind of like a true dual port memory, but you only had single port hardware memory, memory lib map may opt to kind of do some logic fallback there rather than mapping with the hardware it has. Also, if it is a very small memory, it can, if the cost is low enough, it will do that. So if there are any, that's why we do have that the extra step for the the map FFRAM. So if there are any memories left over for whatever reason, whether it's because memory lib map doesn't know how to handle them or because it's decided, okay, use the logic fallback, then those will get mapped there. Cool. Are there any other questions?
Did you see the one from Sam Ellicott about exporting JSON?
So in terms of exporting JSON, so for the kind of that final one and the output.
So he says, how does select command interact with exporting JSON? I like using netlist SVG to generate diagrams because he prefers it to Graphs.
So I'm not sure about the write JSON command. There's a lot happening in here.
Yeah. Do you want me to answer that one?
Yeah, if you have an answer.
Yeah, we just had that come up in an issue recently, so I remember it. So yeah, basically we have just added the dash selected here on write JSON, so you can output only a selection, but there's also the JSON without write underscore in front of it, which allows a selection argument, whereas the write underscore versions don't accept the selection directly.
Yeah. So if you do that help, or if you look on the documentation, so help JSON, you get this part where it has an optional selection at the end. So if you were to write JSON whatever, then it would output just that selection. Or if you're using write JSON, you would need to pass the selected keyword like that, and that will give you just a selection being output to a JSON. I think with the JSON without the write, you do need to specify the -O argument and then give it a name. If you don't do that, it will just emit to the terminal. So if I were to say JSON FIFO, then it outputs to the terminal. So you need to give it that -O argument, whereas with the write JSON, you just, the last argument is the file name. To Christoph, so documentation for this, hopefully I will be uploading just the script at some point, and can hopefully Matt be shared with the recording link. There is also just a link in chat for the example synth page on the documentation. That is a slightly different version of this, but kind of goes through that synth ice40 command in written format if you prefer. Otherwise, the recording of this presentation will be uploaded.
It will go onto our YouTube channel, so subscribe today. Okay, any other questions for Krystine? All right, so let's wrap it up there. Just like to say thanks everybody for coming and attending. Really good to have a nice full house. Thanks again, Krystine, for making a great presentation. And I hope you will have a great Christmas break and a new year. Happy New Year. Until next time. Thanks very much, everybody. Bye-bye.
Thanks, everyone. Bye.